My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to our International Physics webinar. So today it's our 58th International Physics webinar. So good morning to all here in Bangladesh, and good afternoon to all those who are watching this program from Japan. So hope you're well and safe from Corona pandemic. So we are trying our best to adjust with this new normal situation. So we cannot continue our normal academic program inside the campus. So we have to start our online program to continue our academic program. So our Department of Physics, Pabna University of Science and Technology, have already started its online program, including online classes and online international physics webinar. So we have already completed our 57 international physics webinar, and today it's our 58. So today it's a very great day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics, Tokyo Metropolitan University, Tokyo, Japan, in a neutrino physics and high energy physics. And we have with us here today Dr. Osamu Yasuda, Professor, Department of Physics, Tokyo Metropolitan University, Tokyo, Japan, connecting with us from Japan. So he has already connected with us. So I'd like to welcome our professor. So, sir, good morning and good afternoon to your part, and welcome to our International Physics webinar.
Morning.
Good morning. So, we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. So, for those who are new, we'd like to introduce that we have actually divided our international webinar into three parts. First, we'd like to introduce our speaker with all of you, and then we have a time. So in that time, our speaker will deliver his speech, and at the end, we have a discussion session. In that time, anybody can join with us, and you can also ask question by commenting. So I think you have already come to know the title of the today's international webinar, and the title is the phenomenology of neutrino oscillation. So, and our speaker is Dr. Osamu Yasuda. He is currently working as the as a professor, Department of Physics, Tokyo Metropolitan University, Tokyo, Japan. And if we see his educational background, we can see he has completed his BSc degree and MSc degree and PhD degree from University of Tokyo. And if we see his professional career, he got a JSPS fellow from the University of Tokyo from October 1985 to March 1986, KEK, April to August 1986, and also other fellowship and postdoc fellowship, assistant professor, Tokyo Metropolitan University, visiting professor, associate professor, and also professor from 2013 to present. And his research interest, you can see his research interest in theoretical high energy physics and theory of elementary particle physics, natural science, theoretical studies related to particle, nuclear physics, cosmic ray, and astrophysics. And his research history, we can see his research history from 1986 to present. And his research grant, he got a lot of grants from different organizations. And his recent talk in different conference and other program, and his recent publication, you can see. So, and this is his ORCID ID. So thanks all for all of your patience. Now it's time to go to our professor. So thanks again, sir, for accepting our invitation. It's your time, sir. You can start your session.
Okay, so thank you very much for the invitation and the introduction. So, hello everyone. I am Osamu Yasuda, speaking from Tokyo Metropolitan University, Japan. And today I would like to give brief introduction to phenomenology of what is called neutrino oscillations. And let's see, let me go to the full screen and let me change the PowerPoint option. Okay. So in the first part, I would like to give a brief introduction to the standard model of elementary particles. And that means that what are the definitions of elementary particles and what are the interactions of elementary particles, etc. And then in the second part, I will give the brief description about the neutrino oscillation phenomenology. And this neutrino oscillation phenomenology comes from the fact that people have discovered neutrino mass, which is the indication of the physics beyond the standard model. And I will explain all these things in the second part. So anyway, so let me start with the standard model of elementary particles. And what are the elementary particles? Well, that is defined as what cannot be divided further at that period of time. And today, the elementary particles consist of electrons and quarks. And well, let me, as example, let me take the molecule of water. It consists of hydrogen and oxygen atom consists of nucleus and electrons surrounding them. And this nucleus consists of protons and neutrons. And it turns out that these protons or nucleons are called actually nucleons. Nucleons consist of U quarks and D quarks. Well, there are two kinds of quarks at this point. And so these quarks and electrons are supposed to be elementary particles at this point. But actually, that's not the all of the story. And there are other elementary particles called neutrinos. And this neutrino was predicted by a theorist called Wolfgang Pauli in 1933, more than 80 years ago, 70 years ago. And his argument goes as follows, namely, people knew that there are the decay process of neutron into proton and electron. Both are charged particles, so it was possible for them at that time to observe these two kinds of particles. But this process does not satisfy energy conservation and momentum conservation at the same time. So in order to solve this puzzle, Pauli introduced a hypothetical particle called a neutrino, which is very light and it is neutral electrically. So if his hypothesis is correct, then neutrons decays into proton, electron, and neutrino. Well, from the point of the terminology of today's elementary particle physics, this turns out to be anti-electron neutrino. But anyway, it's some kind of neutrino. And 20 years later, neutrino was first discovered experimentally by these people by using reactor neutrinos. And since, as I explain later, neutrinos is very difficult to detect, it took them more than 20 years. And much later on, well, at this point, they were not sure whether neutrinos have mass or not. And for a long time, neutrinos were supposed to be massless. In other words, neutrinos was expected to have no mass. But in 1998, people have discovered that neutrinos have mass, and I'll talk about in detail later. So up this point, here's a summary of elementary particles. The matter consists of quarks and leptons. Leptons is a generic term for electrons and neutrinos, and in this particular case, electron neutrinos. And they are called leptons, which have different properties from that of quarks. Quarks constitute composite particles because of the attractive force between them. But leptons do not feel such attractive force between quarks, and they are called leptons. So they have different properties, and they never constitute composite particles. So actually, that is not the all the story, and there are actually phenomena called cosmic rays. And at the beginning of 20th century, people have discovered that some kind of particles called cosmic rays are falling down constantly on Earth. And actually, it turned out that source of this cosmic ray are the protons or helium nuclei. And actually, so the original cosmic rays are called primary cosmic rays. But since we have air, or in other words, atmosphere, between the space and the Earth, these cosmic rays collide with nuclei in the air, and they produce particles which are called the secondary cosmic rays. They are called pions or kaons, some kind of composite particles of quarks. And then also these secondary particles decay into lighter particles, and maybe strictly speaking, they should be called third cosmic rays, but in general, they are called all secondary cosmic rays. And most of the remarkable thing is that there are particles called muons, and muons have almost the same properties as that of electrons. And the only difference between muons and electrons are that muons have much heavier mass. In other words, muon mass is something like 200 times as that of electron mass. And this muon is called the elementary particles of second generation. So there are generations, first generation and second generation. And the list table here is a table of the first generation. And it turned out that we have all the way up until third generation, first generation, second generation, and the third generation. And we know that there is no such thing like fourth generation, fifth generation. The generation stops at 3. And as I said, the difference between first generation and second generation is the only in mass. All other properties are the same, but the only difference is the mass. If you actually go to the higher generation, first, second, third, then the mass of quarks and leptons become heavier and heavier. And you may have heard the famous formula E equal mc squared by Einstein. And this formula tells us that basically the energy is equivalent to mass. So if you can actually change the mass into energy, it becomes extraordinarily large energy. But differently put, in order to make the heavier particles, you need a lot of energy to produce the heavy particles. So in order to produce second generation particles or third generation particles, we need a special device to produce the large amount of energy to make second generation particles or third generation particles. One other thing that I should mention is that as far as the neutrino is concerned, they are all massless in the standard model of elementary particles. For first generation, second generation, third generation, they are all massless. And another thing in the standard model to mention is that there are things called antiparticles. It sounds like science fiction, but they actually exist. Antiparticles are defined as particles with the same mass and opposite electric charge. So in the case of electrons, the antiparticle of electron is called positrons, and mass is the same, and the electric charge is the opposite. And this notion of antiparticle was developed by Dirac in 1930 when he proposed the equation for relativistically moving particles. And in his case, it was applied for relativistically moving electrons. So it actually takes into account relativity, special relativity, and quantum mechanics in his equation. Now it's called the Dirac equation. And according to this Dirac equation, it predicts not only electrons, but also positrons. And 2 years later, it was discovered that positron exists. And so in general, any particles, 3 generations of quarks and leptons have their own antiparticles. Even the neutrons Neutrons are supposed to be neutral particles, but it consists of U quark and two D quarks. And the U quark has antiparticle as a U anti-U quark, and D quark has antiparticle called anti-D quark. So they have their own antiparticles. So neutron has antiparticles called anti-neutron. They actually were also observed in the experiments. Actually, this number, three generations of quarks, were theoretically predicted a long time ago, almost like 50 years ago, by a Japanese theorist, Kobayashi Masukawa. And they were actually interested in what is called CP vibration. I will mention that in next slide. And in order to actually explain some property of CP vibration, they actually wanted to introduce three generations of quarks. And that was actually even before some of the quarks or leptons were discovered. So it was very good observation in 1973. So this is a kind of different from what I have been talking about. This is the history of the universe. And the universe started as a Big Bang. And the temperature at the beginning of the universe was extremely high, like 10 to 32 degrees. And at that time, the number of particles must be the number of the antiparticles. So there must be an equal amount of matter and antimatter. Matter consists of particles and antimatter consists of antiparticles. Namely, antimatter consists of antiprotons and surrounding by the positrons, and also as well as antineutrons, etc., etc. But now, at present, we know that our temperature is something like 3 degrees. In Celsius, it is minus 270 70 degrees. Now, so in the process of cooling down of the universe, something must have happened between between the particles and antiparticles, because at present, according to the cosmological observation, that we know that our universe is dominated by matter, and there is no such thing like antimatter at all. So in the process of cooling down of the universe, there must have been some process in which there can be some asymmetry between particles and antiparticles. And that was the motivation for CP vibration. CP stands for C stands for charge conjugation, and P stands for parity transformation. And CP is a sequential operation, parity transformation followed by charge conjugation. And if the theory is CP symmetry, namely if it is invariant under CP transformation, it is CP symmetric model. Now, people know that if CP symmetry is broken, then there can be a difference between the speed of the reactions. Heavy particles decay into light particles plus blah, 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 and heavy antiparticles decaying into light antiparticles plus blah, blah, blah. So if CP symmetry is broken, then we may be able to explain the antimatter asymmetry of the universe by theory of cosmology and particles. Because if the speed of these two reactions are different, then it is possible that the first antiparticles decay into light particles first, and then probably they will disappear completely, and we are left with particles, and therefore we may be able to be left with matter only. That's how the argument goes. So let me summarize so far. Elementary particles or matter particles consist of quarks and leptons, and there are antiparticles like antiquarks or antileptons. But today, our universe is dominated by matter only without any antimatter asymmetry. And if there can be some difference between these and the particles, we may be able to explain this asymmetry. So let me go to the interaction of the elementary particles of the standard model. So in principle, there are four kinds of interactions between elementary particles: strong force, electromagnetic force, weak force, gravity. And they are actually mediated by the so-called intermediated bosons. And by uh, throwing a ball and catching a ball, they actually transfer the force. In the case of strong force, it's called gluon. Strong force stands for the nuclear force between protons and neutrons, etc. Electromagnetic force is very familiar, and it's a Coulomb force. Weak force stands for the decay of neutrons, for example, and it's not so familiar in our present life, but it is important, particularly for neutrinos, which I'll explain later. And in case of gravity, it's so weak that we can forget about gravity completely when we discuss elementary particles. So standard model treats only three forces, and we always ignore gravity in the case of elementary particle interactions. So in the case of neutrinos, since it is a neutral particles, it does not feel electromagnetic force, and it does not feel strong force, because leptons do not feel strong force. Only quarks feel strong force. So in the case of neutrinos, it doesn't feel strong force, it doesn't feel electromagnetic force. The only the force it feels is a weak force and gravity, and we can forget about gravity. So the only relevant force is weak force. And flavor, there are notions called flavors. Flavor of neutrinos, nu e, nu mu, nu tau, is actually speculated by observing an outgoing charged leptons in the reaction like this. If we hit neutrinos by neutrons, then we get electron. If we hit neutron by nu mu, then we will get mu minus. Or if we hit neutron by nu tau, we get tau minus, etc. And if hit neutron by antineutrinos, nu e bar, then we get the positron E plus, and mu bar, mu plus, mu tau bar, tau plus, etc. So by these reactions, we can guess what the original neutrinos were. So basically, that was the summary of the standard model, and let me go on to the second part, namely neutrino oscillations. And so far in the standard model, neutrinos are supposed to be massless. The mass of neutrino is completely zero for certain reasons in the standard model. But as I mentioned, in 1998, people have discovered that their neutrinos have mass. So theories should be modified. So from now on, I will talk about physics beyond the standard model and neutrino oscillation, because neutrino oscillation is one of the phenomena which is predicted by physics beyond the standard model. And neutrino oscillation is, in a word, the phenomena of quantum mechanical interference. It's just like the interference of two different waves. So as I said, in the standard model, neutrinos are supposed to be massless, but beyond the standard model, neutrinos have mass. And there is a notion called flavor eigenstate or mass eigenstate. And in the case of massless neutrinos, they are basically the same. But when we turn on the mass of neutrinos, flavor eigenstate can be different from mass eigenstate. And mass eigenstate is the state in which the mass of each neutrino can be defined. So let me call mass eigenstate as nu1, nu2, nu3, and the mass of each mass eigenstate must be M1, M2, M3. And so this is a matrix notation, but flavor eigenstate, nu e or nu mu or nu tau, is a linear combination of this mass eigenstate, nu1, nu2, nu3. So let me now explain what the neutrino oscillation is. Actually, the simplest scenario was discussed by actually three Japanese physicists, Maki, Nakagawa, Sakata, in 1962. It's more than 50 years ago, and they actually introduced the flavor eigenstate and mass eigenstate. And in the case of toy model, two generations, this unitary matrix can be a 2 by 2 orthogonal matrix, which is actually a rotational matrix. The theta is called the mixing angle. And if theta is non-zero and if mass of mass eigenstates are non-zero, then it turns out that the probability of transforming one flavor eigenstate into another can be expressed as this formula. It is proportional to sine squared 2 theta times sine square with some argument. Arguments is delta m squared. Delta m squared meaning the mass square difference. In this case, m2 square minus m1 square times the distance L. The neutrinos have to fly from one place to the other. The distance is called L. And the neutrino has energy, so it has to be divided by energy. And so actually, if you plot the probability as in terms of the distance L, it behaves like this. The probability of nu mu to nu mu behaves like this red line, and the probability of nu mu to nu tau behaves like blue line. And it takes actually 300 kilometers. It's a long, long distance, considering the fact that it is a phenomena of elementary particles. It's a very huge macroscopic distance. But anyway, it has oscillatory behavior like this. That is the reason why it is called a neutrino oscillation instead of neutrino flavor transition or something. So actually, at present, we know that we have delta m square like 3 times 10 to the minus 3, as I mentioned later. And in that case, if we choose energy to 0.6 GeV, GeV stands for 10 to the 9 electron volt, giga electron volt. And this is a typical for the accelerator neutrino physics. And then this maximum oscillation probability is obtained at distance 300 kilometers. On the other hand, if we have a 4 MeV, mega electron volt, 10 to the 6 electron volt, this is in the case of reactor neutrinos, which I will mention later, then 2 kilometers gives you the maximal oscillation probability, etc. But anyway, so if we have neutrino mass and mixing, then flavor transition phenomena occurs. And as I mentioned before, macroscopic distance, like 300 kilometers, is required to see this phenomena. So it's actually huge setup for the experimentalist to put the detector and fit it much, much farther away from the source of neutrinos. Actually, this was a story in vacuum, and this actually describes what happens in matter. In the case of the phenomena in matter, there is an additional process. Namely, in matter, we have electrons in matter, and there is a so-called charged current interaction between electron neutrino and electrons in matter. So in this case, only electron neutrinos have a special component. So we have additional contribution like this in the equation of motion. And in this case, the conclusion is that it behaves like similar probability formula like this, but theta is replaced by theta tilde, and delta m square L over 4e is replaced by delta e tilde. Delta e is defined like this, and delta e is defined as delta m square divided by 2e, etc., etc. So there can be some difference between the oscillation in vacuum and oscillation in matter. So now let me go to the concrete examples. First, let me talk about atmospheric neutrinos and accelerator neutrinos. So this is again about the cosmic rays. As I mentioned previously, actually, primary cosmic rays are falling onto the ground constantly, and they collide with nucleons in the atmosphere, and they produce secondary cosmic rays, pions or kaons, and pions decay into muons plus nu mu, and muons immediately decays into electron plus nu e plus nu mu bar. And in the case of pi minus, it decays in mu minus and mu plus nu mu bar, and mu minus decays into electrons plus nu e bar plus nu mu. And so if you forget about the difference between neutrinos and antineutrinos, as far as the nu mu or nu e is concerned, the number of nu mu type and the number of nu e type must be 2 to 1 if you look at this reaction chain. But in reality, according to the experiment, the observational ratio something like 1.3 to 1, which actually disagrees with this prediction. So what was wrong? So the conclusion was that because of the neutrino oscillation between nu mu and nu tau, nu mu decreases. And well, actually, this was confirmed by Super Kamiokande experiment in Japan. And well, so basically, as I said, the probability formula looks like this, and it depends on the length of the path of neutrinos divided by the energy of neutrinos. And theta and delta m square is a given number we cannot change, but depending on the neutrinos property, we can change the L and E. And this formula is consistent with observation at Super Kamiokande, which is a water Cherenkov detector like this. And that was actually confirmed in the year 1998. That was the first experiment in which neutrino mass was confirmed. And after then, a lot of experimentalists did accelerator neutrino experiments. The first one was called K2K, and sorry, something was wrong with this. Sorry about this. There is some font problem. So K2K to Super Kamiokande, and there is another American experiment called Minos, and that actually comes from Fermilab National Fermi National Accelerator Laboratory to Sudan Mine in Minnesota, United States, or in Europe, Opera. CERN is a laboratory in Geneva, and they actually injected neutrinos from CERN to Gran Sasso. Gran Sasso is an underground laboratory in Italy. They all are consistent with atmospheric neutrino experiments. And also, there are also other experiments in operation. T2K is the extension of K2K in Japan, and Minos Plus and the Nova, they are all experiments in the United States. They are all consistent with the atmospheric neutrino experiments. So now let me go to solar neutrinos and the long baseline reactor neutrinos. It has been known that the reason why we get so much energy from the sun is because there is a fusion reaction is going on in the sun. The fusion reaction tells us that 4 protons actually goes to a helium nucleus plus 2 positrons and 2 new electron neutrinos plus some energy. And this electron neutrinos are called the solar neutrinos. And the huge amount of neutrinos are produced constantly in addition to the heat. So in addition to the light or heat which we are receiving from the sun, we must be receiving a lot of electron neutrinos from the sun. So that was first detected by Ray Davis here. And he started his experiment in the 60s. And he observed the flux, which turns out to be something like 1/2 or even less than 1/2 of the theoretical prediction. And that was called the solar neutrino problem. And it turned out that the flux of neutrino, nu E, is reduced because of the conversion of nu E to nu mu and nu E to nu tau. And much later on, there was a Canadian experiment called SNOW. SNOW stands for Sudbury Neutrino Observatory, and they are actually using the heavy water, which comes from the heavy water nuclear power plant in Canada. Canada has a lot of heavy water in the project, so that was the advantage of Canadian physicists had. And actually, with this experiment, they can actually do the two things. One thing is a nu E plus deuteron. Actually, heavy water is defined as D2, or D stands for deuteron. Instead of ordinary proton or H, they got deuteron. Deuteron is a bound state of proton and a neutron. So this deuteron is actually disintegrated by nu E, and it actually, in the process, one neutrino, a neutron, becomes a proton. So 2 protons plus electron. So this only happens for nu E. And on the other hand, there's another reaction called the neutral current interactions, and the deuterons are again disintegrated by neutrino. But in this case, it can be any neutrino, nu E, nu mu, nu tau. So this happens for all neutrino, which I denoted as nu x. And from this data of 2 reactions, Snow group concluded that nu E plus nu mu plus nu tau agrees with the theory, but only the amount of nu E is less than the theory. So that means that part of nu E are converted to a mu and nu tau. So this is the evidence of neutrino flavor transition in the case of solar neutrinos. But half a year later, there was another experiment called kamran. Kamran is a Japanese experiment which actually is located in the same place as Super Kamiokande. And they were measuring the anti-electron neutrinos which are produced by a bunch of nuclear power plants in Japan. Right now, most of them are shut down because of the nuclear accident in the year 2011. But before 2010, they were actually in full operations. So even though they are far away, like 200 kilometers away from the nuclear power plants, these cameras were actually measuring nu E bar precisely. And according to this neutrino oscillation formula, they were actually able to determine the theta and delta square like this. So basically, the details of the solar neutrino problem was solved. But unfortunately, this experiment came out later, half a year later after this snow experiment. So the Committee of Nobel Prize in Physics actually concluded that this is a kind of a derivative of the snow data. So Atsuto Suzuki didn't get Nobel Prize, and only Art McDonald and Takaaki Kajita got Nobel Prize. So now let me go to the short baseline reactor neutrinos. Reactor neutrinos are actually reactors. What is going in the reactor? Basically, it's a chain of decay of neutrons. Neutrons decay into protons and electrons and nu E bar. And of course, protons and electrons are charged particles, and they are actually protected by the concrete shield. But Nui bar actually escape, and it's totally harmless, but there are a bunch of Nui bar near the reactors. So it was possible for experiment to detect these Nui bar near the reactors. So in the case of short baseline reactor neutrino experiment, the energy is something like 4 MeV, 4 times 10 to the 6 electron volt. So in order for this argument to be something like over 1, the L has to be something like 2 kilometers. And there are three short baseline reactor neutron experiments around 2010. And these 3 neutrino experiments gave almost the same answer. And one of the most impressive results was Diabei in China. Diabei is a place near Hong Kong, and they got a bunch of nuclear power plants there. And because of multiple detectors at the site, they were able to give the error as much as possible, as small as possible, like this. So let me now combine all these facts into one picture, namely 3 flavor neutrino oscillations. So strictly speaking, when I introduced neutrino oscillations, I was actually mentioning the toy case, namely 2 generations. But in reality, there are 3 flavors of neutrinos, so there must be 3 mass eigenstate of neutrinos. So it is actually related by 3 by 3 unitary matrix, and this 3 by 3 unitary matrix is parameterized as 3 orthogonal matrix, theta 2, 3, theta 1, 3, theta 1, 2, along with one CP phase. CP phase turns out to be the CP violating phase, which I mentioned before, which has to do with CP violations, which I mentioned before. And since there are 3 mass eigenstates, we can have 2 independent mass square differences, namely delta m squared 3, 2, which is denoted by green, and delta m squared 2, 1, which is denoted by pink, like this. And delta m squared 3, 1 is the sum of these 2 things, so it's not the independent quantity. So actually, the thing to note is that there is fortunately 2 factors. One is mass hierarchy. The one of the mass square difference denoted by solar neutrinos turns out to be much smaller than the delta m squared of the atmospheric neutrinos. So using this hierarchy, this simplifies the oscillation probability a lot. And also, as I didn't mention, but the mixing angle, which was measured by short baseline reactor neutrinos, turns out to be theta 1, 3. And the theta 1, 3 is relatively small compared with others. So in the Delft approximation of the analysis, we can put theta 1, 3 to 0 in the first approximation. So that further simplifies the analysis. So in that case, basically, solar neutrino and atmospheric neutrinos are reduced to the 2 flavor case, namely as I mentioned before, it's actually reduced to the toy 2 flavor state case. So in that case, we can actually apply the 2 flavor analysis to get the value of delta m squared and sine squared 2 theta. And in this case, in the case of solar neutrinos, the smaller mass square difference is 8 times 10 to the minus 5 electron volt square, and the mixing angle is given by sine squared 2 theta 1 to something like 0.8. And in the case of atmospheric neutrinos and accelerated neutrinos, the mass square difference is something like 3 times 10 to the minus 3 electron volt square, and sine squared 2 theta 2, 3 is almost 1. And as I mentioned before, from the short baseline reactor neutrino experiment, we have sine squared 2 theta 1 3 as something like 0.08. So basically, a lot of information has been obtained in the last 20 years, starting from the Super Kamiokande result in 1998. And here is some of the recent results from T2K accelerator neutrino experiments. And actually, I actually forgot to mention. Well, actually, I have to go to the present status this case. Yeah. So as I mentioned, three mixing angles have been almost determined, and the two mass square differences are also determined. And the only unknown parameters right now is, for example, the mass hierarchy pattern. Actually, this in this case, this is called the normal hierarchy or normal ordering. The heavier state is much heavier than other two lighter states. And in the other case, inverted hierarchy or inverted ordering, the two actually massive states is heavier than the remaining one. And in this case, it can be represented as a positive delta m square 32, and this is a negative delta m square 32. And right now, both patterns are allowed. So this is one one of the unknown things. And the other one is a CP phase delta. It's not necessarily measured precisely. Now let me come back. So according to the recent result by T2K accelerator neutrino experiments, this actually figure shows, actually this vertical line delta chi square corresponds to the goodness of fit, and the vertical axis is the CP phase delta. So it actually plots from minus pi to pi. So something, sorry, minus pi to pi, yeah, minus pi to pi. And so the best fit is somewhere like delta equals minus pi over 2. And this light blue curve corresponds to normal hierarchy, and this orange curve corresponds to inverted hierarchy. So normal hierarchy gives a slightly better fit compared with inverted hierarchy. And CP phase delta seems to be near to minus pi over 2. And this, for example, pi delta equal plus pi over 2 seems to be disfavored at this moment, although it is not completely disfavored. So we need more data, or maybe we need bigger experiments in the future to be conclusive. Also, this is other recent work, and there seems to be some tension between the Japanese neutrino accelerator experiment and the American neutrino experiment called NOVA. According to NOVA's result, this blue curve seems to be the data, and for normal hierarchy. And this blue curve with dashed line seems to be the inverted hierarchy. So as far as NOVA is concerned, inverted hierarchy seems to be favored. But if you combine NOVA and T2K, it is actually represented by black line. So this is a combined result for the normal hierarchy, and this dashed curve black line corresponds to the inverted hierarchy. So if that's the case, maybe if in the case of normal hierarchy, delta equals minus pi or plus pi seems to be favored. And if you stick to the CP phase delta minus pi over 2, then inverted hierarchy gives a better fit. So it's there are a lot of controversies and confusions, and we need more data to be conclusive. So let me now go to the future plan. So as I mentioned, we are still not sure what the which mass pattern is preferred or what the value of CP phase delta is preferred. So in order to determine them precisely, two actual experiments have been proposed and now they are under construction. One is called T2 hyper K. This has the same accelerator in Japan, and the detector will be upgraded version of Super Kamiokande called Hyper Kamiokande. So it's called T2 hyper K. The energy and the baseline length are almost the same as today's T2K experiment. And the other one is the Dune in United States. This is a long baseline experiment from Fermilab to a Homestake laboratory in South Dakota. And this is a place where the Ray Davis measured the solar neutrino for the first time. And they have higher energy and with longer baseline like this. And they are expected to measure the mass pattern and the CP phase delta precisely. So this is a sketch of the pizza hyper-K. This is a so-called JPAC complex with a lot of intense accelerator and sending the neutrinos to hyper Kamiokande, which is 10 times as large as super Kamiokande. On the other hand, this is a Dune experiment, and this is a Fermilab in the suburb of Chicago, and they are sending neutrinos to Sanford Lab in South Dakota. And the baseline length is 1,300 kilometers, and they actually are supposed to measure, among others, the mass pattern very precisely. Now, in the remaining time, let me talk about the beyond the standard scenario, namely beyond the standard model with three massive neutrinos. Well, actually, in general, high precision measurement like T2 hyper-K or Dune experiments, it is expected that high precision measurements of neutrino oscillations can be used not only to measure the parameter in the standard case precisely, but also to prove the physics beyond the standard model with massive neutrinos by looking for the deviation from the standard scenario. So this is one of the motivations. And the other motivation is that there are several actually phenomena which seem to contradict or contradict with the standard scenario. Namely, well, I will explain that later, but so in order to explain that phenomena, two actually scenarios have been actually pushed forward. One is so-called light stellar neutrino. Stellar neutrino is defined as neutrinos which do not even feel weak force. Well, ordinary neutrinos feel at least a weak force. That is the reason why we can detect them. But stellar neutrinos do not feel any force at all among all three forces in the standard model. They only feel gravity. And the other one is non-standard interactions, and neutrinos interact with other fermions like U quark or D quark or electrons. And then they have to produce neutrinos with different flavor, which does not occur in the standard model. And the magnitude of this scenario can be as large as 10% or in some cases as large as 100%. So it may be possible in the future experiment to detect those scenarios. But one thing I should mention is that neither stellar neutrino nor non-standard interaction is required from the theory, from the first principle. They are just introduced phenomenologically. Well, maybe that is the reason why the title of my talk is Phenomenology of Neutrino oscillations. Basically, all these things actually introduced phenomenologically to explain certain anomaly. So let me first of all describe the light neutrinos. Well, actually, there are several experimental indications like LSND anomaly. LSND anomaly was the result of the accelerator experiment in the 1990s at Los Alamos experiment. And they actually found certain neutrino oscillation signal for 50 MeV and 30 meters. And another thing is that the reactor anomaly. And if people look at the old data with the reactor neutrino experiments with 4 MeV and with a baseline 10 meters, 10 meters is extremely small, and they're actually putting detectors just beneath, nearby the reactor core. And they seem to be observing some deficit of nu bar. And the gallium anomaly is kind of a calibration of solar neutron experiment. And they also observed some deficit of electron neutrinos inside the uh, source of neutrinos in the detector. So in order to explain these deficits or neutrino oscillations, it is necessary to assume that delta m square must be of order 1, which is much, much larger than the delta m square of atmospheric neutrinos or delta m square of solar neutrinos. And the other thing is that if we have a fourth flavor eigenstate, we must have a mass eigenstate. We must have a fourth flavor eigenstate. But we know from the LEP experiment. LEP experiment is a large electron-positron collider at CERN in 1990s. And they actually discovered that number of neutrinos coupled to Z bosons. In other words, number of neutrinos which actually feels weak force must be 3. By looking at this data, number of neutrino 2 or number of neutrino 4 does not fit to the data. So they concluded that the number of neutrinos coupled to Z boson must be 3. So in order to be consistent with these constraints, the fourth flavor eigenstate has to be stellar neutrinos, which does not feel weak force at all. So that is the reason why it is called stellar neutrinos. Well, there are two kinds of patterns, 2+2 scheme like this, or 3+1 scheme, but let's see, I'm kind of running out of time, so I have to skip some of the details. Well, actually, it turns out that both scenarios have some kind of tension. In the case of 2+2 scheme, it has tension depending on this parameter, but if you combine the solar neutrinos with atmospheric neutrinos, no matter what this parameter has, what kind of parameter this value has, it gives us a very bad fit. So this is completely excluded by solar neutrinos and atmospheric neutrinos. And in the case of 3+1 scheme, there is also tension between nu mu to nu mu. This is called the disappearance experiment. Also, nu bar to nu bar. This is also disappearance experiment. It is possible to derive certain kind of inequality for between the disappearance experiment and the appearance experiment. For example, LSND, nu mu bar to nu bar. We have to have this kind of inequality, and this means that in this allowed region, sine square 2 theta and delta m square, this allowed region in the gray region is allowed region for LSMV experiment, for example. And if in order for this inequality to be satisfied, this gray region has to be left-hand side of the green curve. But that is not the case. So it's kind of excluded. This is a recent status of the exclusion. At 90% confidence level, it's almost excluded, but if you go to 99% confidence level, there may be some hope. But one thing which is clear is that there is a tension between these data. So finally, non-standard interaction. As I said, non-standard interaction changes the flavor from nu alpha to nu beta with the same phenomenon F. And if this is the case, it can actually gives us extra contribution to the matter effect. Matter effect only, in the standard case, matter effect only appears in the new case, but in this case, it appears everywhere, which is denoted by epsilon alpha beta. And one of the motivation for us to introduce non-standard interaction is that there seems to be some tension between solar neutrinos and kamran data. And if we believe that both are consistent, then the energy spectrum, actually the solar neutrino energy versus this neutrino oscillation probability has to behave by the black line like this. If we adopt the mass square difference measured by kamran, this should behave like this. But according to the recent data by Super Kamiokande and Snow, this actually does not, even though energy decreases, it does not actually go up like this. It seems to be constant rather. So that is called no upturn is observed when we actually lower the threshold energy of solar neutron energy. So these different curves are represented by non-standard interactions, green curve or red curve. So that is the reason why this actually gives us a motivation to consider non-standard interactions. And according to some people's result, this best fit is located here, and the standard case is somewhere here near the boundary of 90% confidence level. So it is not, standard case is not completely excluded yet, but non-standard interaction seems to be favored. And also in the future, there is some possibility like a hypercamufande to observe this non-standard interaction, which I have to skip. So actually, I'm getting out of time. So well, let me just say that there are a lot of implications of the discovery of neutrino mass. And neutrino mass is, first of all, the evidence of the physics beyond the standard model. So it gives us a clue for beyond the standard model. And the neutrino mass is much, much lighter if you actually look at this table in the log scale of mass. Neutrino is much, much lighter compared with quarks and leptons, charged leptons. So there is some mystery for the mass hierarchy. And one other thing is that the CP phase, the CP delta, stands for the difference between neutrinos and antineutrinos. And this actually expected to gives us a clue between the matter-antimatter asymmetry of the universe. Well, I have to skip this thing. And well, as far as the recent development of neutrino oscillation experiments are concerned, a lot of neutrino oscillation experiments have been performed, and we can determine the three mixing angles and two mass square differences. And the remaining task is to determine the CP phase delta and the mass pattern. And there are two accelerator experiments going on in Japan and the United States. And new physics can be investigated by looking for the deviation from the standard scenario of these experiments. Okay, that is. Thank you very much.
Thank you, sir, for your nice presentation, sir. So, sir, we have got some questions. So, if you allow, we can read it out. So, what will happen when the CP symmetry is broken,
if
sir?
CP symmetry is broken,
So
there is a difference between a reaction for neutrino oscillation for neutrinos and antineutrinos. And although it does not necessarily mean that it can be directly applied to the early universe, it actually gives us a clue for how the CP violating process would have been realized in the process of early universe.
thank you, sir. So we have another question. So does the dark matter has antiparticle properties?
Yes, actually we do not know anything about dark matter yet, but of course, if from the principle of relativity and elementary particles, dark matter must have antiparticles. But it is also possible that dark matters, the antiparticle of dark matter is dark matter itself. It is called Majorana particles. But anyway, since we don't know anything about dark matter yet, in general, we expect that there are dark matter particles and antiparticles of dark matter particles. Hello?
So why the temperature of the universe decreasing with time, as the increasing the time from the Big Bang?
Well, because, oh, sorry.
So why? Yeah, you can start.
Well, the reason why it decreases is because the universe actually expands, and that is a equation of motion in the thermodynamics.
Okay, sir. So thank you, sir. So but there is another question. What is mixing angle, sir?
Yeah, actually, that's a good question. Let's see. Mixing angle. Can I share?
Yeah, of course.
So, first of all, as I said, in the presence of neutrino mass, flavor eigenstate are different from mass eigenstate, and they are linear combination of these things, mass eigenstate. So that is the reason why unitary matrix comes in. And in the case of 2 by 2, or 2 by 2 matrix or 2 flavor case, it is orthogonal 2 by 2 matrix, and it is parameterized by mixing angle. So it actually is an indication of the fact that flavor eigenstate is a linear combination of mass eigenstate. And in this particular case, it is just simply parameterized in terms of one parameter.
Okay, sir. So thank you, sir. So we have another question. So maybe the last question is, how can we produce second and third generation of quark?
Sorry, how can we produce what?
Produce a second and third generation of quark.
Yes, that's a good question. Yeah, so as I said before,
I have already explained.
so so the second and third generations are very heavy, and it's actually second and third generation quarks are very unstable too, and it will quickly decay into lighter quarks like U quark or D quark. So in a very short period of time, it will be produced by high energy environment. So if you hit particles with antiparticles, and at one time we got a lot of energy, extremely high energy in an accelerator, and then that energy can be used to produce the second generation heavy quarks or third generation heavy quarks. And actually, the first example of such cases was the accelerator experiment just after the World War II in the United States. And they actually produce a bunch of strange quarks by using accelerators. And the reason why they could produce a bunch of strange quarks was because they actually created a lot of high energy particles in accelerator, and they were used to produce heavier particles like the strange quarks, etc., etc. And actually, at the end, the sixth quark called the top quarks, it was extremely heavy, and it requires extremely large accelerator at Fermilab, and finally they increase energy all the way like 1 TeV, namely 10 to the 12 electron volts, etc., etc., and finally they were able to produce such heavy particles. And that is how they produce heavy particles.
Thank you, sir. So we should conclude our discussion session. So as there is no question. So thanks, sir, for your wonderful presentation and discussion session. So we'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So I think the students have learned a lot of things from your session, sir, about neutrino physics and neutrino oscillation and its phenomenology. So hopefully in near future we'll arrange another webinar with you, sir, if you have time, sir. Thanks again. So bye for today.
Okay, so thank you very much.
Thanks.
Bye-bye.
Thanks. Bye.